Hey everyone, welcome to another week of mini lecture. This week we'll be covering linear programming and network flow. So linear programming is another general tactic to solving a large class of problems. If you can formulate some problem as a linear programming problem, you should be really happy about it because we have a general algorithm, as you'll see, to any linear programming problem. And here's the motivation for using LP. In life, we're often optimizing something. Maybe you're maximizing sleep time, or minimizing cost, or maximizing the number of days you can skip lecture. All these things, but they're subject to some constraints. For example, you can't sleep for more than 24 hours a day or less than 0. I mean, these are silly examples of constraints, but you kind of get the idea that there are two basic ingredients to LP problems. There's the objective function and the constraint. So objective function is whatever you're maximizing or minimizing, whereas the constraints are things you have to satisfy while maximizing or minimizing the objective function. Okay, so the first question you might be asking is, given a bunch of constraints and some objective function, is it always possible to find an optimum to the objective function? And the answer is no. So there are actually two ways that you can fail to find an optimum. One of them is that the constraints make it infeasible. Big word here. Infeasible just means that suppose I want to maximize x, and my two constraints are x is bigger than 1 and x is smaller than -2. You can see that there's no value that x could take, so there's no reason to maximize it. So this is an infeasible linear program. On the other hand, you can have something that's too good, unbounded. So similarly, you can have maximize x, and my only constraint is x is bigger or equal to 0. Well, x could be, anything like as big as you want, so there's no real maximal value for x. So these are sort of two extreme. One of them, there's no values you could take. The other one, there are too many, and they just get bigger and bigger. So these are the two ways that you can fail to find an optimal solution for a linear program. But as we can see, there are a lot of cases where we actually can. So let's dive into a motivating example for a case that you can actually find the optimal solution. So here's an, I don't know, eerily realistic question I just made up on the spot. You need to study today. Every hour that you spend on a non-CS170 class, CS170 class, will give you 1 unit of happiness. But every hour spent studying for CS170 will give you 2 units of happiness. You can't study more than 7 hours for each class, and you have a budget of 12 hours. How do you maximize happiness? Okay, so there are a couple ingredients in this problem, right? You want to look for an objective function you're trying to maximize or minimize, and you're trying to look at constraints. So let's look at, let's first put some variables to this. Let's say that you spend x1 amount of hours on this other class and x2 hours spent on CS170. So this just enables us to sort of put these like constraints into equations rather than just words. All right? So what's the objective function? The objective is to maximize happiness right here. Right? I encourage you to underline whatever objective you have. It's always helpful to just remind yourself what you're trying to do. So the objective is to maximize x1 plus 2x2. Why is it x1 plus 2x2? Well, the happiness that the other class brings you is 1 unit per hour. So it's x1. And the CS170 will give you 2 units per hour. So that's 2 times x2. So that's what you're trying to maximize. Now you have some constraints. What are the constraints? Let's see. First of all, you can't spend more than 7 hours on either class. Right here, right? You can't study for 7 hours for either class. So we have x1 and x2 are both smaller or equal to 7. Now you have a total budget of 12 hours. So that means put together, you can't spend more than 12 hours studying for these two classes. So you have x1 plus x2 is smaller or equal to 12. And now the last one is a little bit silly, but this is something that when I'm doing these, I always forget about. It's the one that says you can't spend negative hours studying. A lot of these questions will have these constraints of, you want positive numbers or you want negative numbers, that sort of just is common sense. It's not necessarily mentioned in the problem, but it's common sense that you can't spend a negative number of hours studying. If you can, please contact me. I would love to know. But for the time being, we'll say that x1 and x2 are bigger than 0, bigger or equal to 0. So you might be seeing that I have this, I don't know, Cartesian plane drawn on here, and I want to just pause for a moment and just look at these constraints. They're all linear. That's why we have that's why this is called linear programming. If you have nonlinear equations, you can still formulate it as sort of this like structure, but the algorithm that we're introducing in linear programming will no longer work for those. So for linear programming, we ask that the objective function is a linear combination or a linear function of the variables that you introduce, and then the constraints are all linear inequalities or equalities. So in this particular problem, we didn't have any equalities, but yeah, you can sort of imagine that you can also have equalities. Okay, so now that we've dealt with linearity and we've dealt with the objective function as well as the constraints, we can try to solve it. And one of my favorite ways of looking at a linear programming problem is to plot them, because one of the great things about having a linear equation is that we know exactly how to plot them. So let's look at the constraints first. We have x1 is smaller or equal to 7, so we have 7 here maybe, and we'll draw a line. Maybe I'll use a different color. Let's use a different color. Spice this up a little bit. Okay. I have x1 is smaller or equal to 7, which means that all the area to the left of this line is feasible. Now x2 is also smaller or equal to 7. So we have x2 here, put 7, and I have this line. So the feasible region will now have to be under. So now, given these two constraints, we know that the feasible region is like right here, right? It has to be to the left of this line, to the left of this x1 smaller or equal to 7, and then to the below this other line, this horizontal line. I'm realizing that you can't actually point on the screen because you won't see the mouse. All right. So now our next one is x1 plus x2 is smaller or equal to 12. Okay, so let's draw this line. Oh, I might be butchering this a little bit. But imagine this is 12. So this is 12 and this is 12. And now the feasible region has to be under this new line that we've drawn. Now x1 and x2 are both bigger or equal to 0, so we have, these lines. And we can see that the region that satisfies all of these constraints is this region right here. Oh, so large. Okay. Let's see. Right here. Right. This region is the only place on this plane that satisfies every single equation that we've outlined so far. So any point in this region will satisfy the constraints, and now our goal is to ask ourselves, where in this region can we maximize x1 plus 2x2? Now let's draw x1 plus 2x2 in as well. So what is x1 plus 2x2? It's, if you set it equal to some number k, and we don't know what k is, we get this line. What does this line look like? Well, let's see. It looks, I think, something like this. Right, it should have slope, okay, hang on. It should have slope -1/2, if I'm not mistaken. And depending on what k is, right, this line can move parallel to just, I don't know, they can shift up and down on this graph, but have to be parallel to the previous. And we see that, what is k? K is sort of the distance between the origin to that. So we're trying to maximize the value of x1 plus 2x2, and essentially what happens here is you want to push k as far as possible, right? So essentially what I'm saying is that on the same line, on the same green line, any 2 points on the same line will have the same objective function value, whereas if you lie on different lines, then you'll have probably a different objective value. So now we're in trying to optimize, we're trying to push this line to a maximum. And so you might be guessing that we just have to push it as far as possible, and you would be correct. Now, this is a little bit hand wavy, and you might be complaining about this, but actually, in the next segment, Neil will give us a quite exact solution or precise solution, rigorous one, to why we can do this. But for the takeaway for this video, I just hope you can understand that given these constraints and this objective function, we can draw on a graph with a feasible region. So the feasible region is all the points that satisfy the constraints. And then inside the feasible region, we're trying to maximize or minimize the objective function. And the objective function is also a linear line. All right, that's it for this segment. I'll pass it off to Neil now.
Thanks, Lily. So with this understanding of linear programming, let's get into actually solving linear programming problems. And so just to recap, the two main goals of linear programming are one, satisfy a set of equations or inequalities, also called constraints. And then two, we want to maximize or minimize some sort of objective function that we care about. And so one key fact that we're going to understand first is that when solving linear programming problems, we'll see that the optimal value is found at a vertex. It's always found at a vertex, or it's found at an edge, right? And so what do I mean by this? When we're visualizing linear programming problems, when we graph it out, when we graph out constraints and stuff, we'll see that the optimal value that maximizes or minimizes our objective function to the maximal capacity, that's always going to be found at a vertex. So it kind of breaks our problem down simpler, right? Now we only have to look at the vertices of our graph once we graph out a linear programming problem, and we'll get to how exactly that works in just a bit. But I just want to clarify the statement. So the optimum is always found at a vertex, or basically like the edge of the polygon once we graph out a linear programming problem, with two exceptions. One is if we have infeasible constraints, which is basically constraints that kind of conflict, right? And this is kind of like a trivial example, but if we have a constraint that's like x is greater than 1, but we also have another constraint that's x is less than 0, we're obviously not going to be able to find a solution, period, solution to this linear programming problem at all, right? So we won't have an optimal value. The second second exception is if our problem is unbounded. And what that means is if we have again, really simple case, but if we have an objective function that says like maximize x, but the constraint is like x is greater than 0, right? We can set x to be arbitrarily large. So except for these two cases, we'll see that the optimal value is found at a vertex. And so kind of, diving into an example, let's say, again, this is straight from the textbook, but let's say we have this objective function, maximize x1 plus 6x2. And we have a bunch of constraints, right? x1 is less than or equal to 200, et cetera, et cetera. And if we graph out these constraints, we'll get this diagram. And so the kind of shaded region represents the feasible region, right? Solutions, points in this, region would satisfy all the constraints. But the thing is, we don't know that they're optimal points, right? Again, we're trying to maximize x1 plus 6x2. So we need to find the point, x1 comma x2, such that this objective function is maximized to the, to the most. So how do we do that? Above, I mentioned that the optimal value is always found at a vertex. And so what we can do is we can then you see this polygon-esque shape, right? With different vertices. All we need to do now is explore the vertices and see, kind of go about that, right? So checking out the vertices, the first one is this point, the trivial point 0, 0. If we plug that into our objective function, we'll get 0 plus 6 times 0. So the value of this point, this vertex, is just 0. The value of the next vertex is 200, 0. If we plug that into the cost again, we'll just get 200. And if we do that, the same thing for here, it'll be 200, 200. So if you plug that in it's like 1400. And same for this, it's 1900. And this, I think, is 1800. Again, I'm just plugging in the vertices into the objective function. Oops. Right? Just kind of plugging and chugging. And so now, sorry, I forgot to mention this algorithm is called simplex method, right? Um, anyway, so how simplex method works is we're gonna iterate through all of the vertices, right? We can start from any arbitrary vertex, right? For this case, let's just start at 0, 0, right? This one. So now you iterate through the vertices, you kind of calculate, what do you get when you plug in this vertex into the objective function. And then once you hit a vertex, that's kind of a local maximum or a local minimum, depends on what your objective function is. Once you get to a vertex that has no better neighbors, which means it's a local, optimal value, then you're done. So essentially, what this is saying is that a local optimum, a local optimal value equals global optimal value in this case. And so that might be kind of surprising because in a lot of cases, this is not the case. Um, but in linear programming systems, it is, and we'll see why, right? So, let's just follow this algorithm. Let's pick an arbitrary point. Let's say this 0, 0, and let's iterate through the vertices in let's just say counterclockwise order. And, the first vertex you hit is this one. You plug it in, you get 200. Let's check out its neighbors, right? So the neighbor of this, you kind of go here and you check out this vertex, it's 1400. Okay, so now we see that the neighbors of, you know, 200 comma 0 are, they evaluate to 0 and 1400. So it's not a local optimal yet. So we have to keep searching. So we go to this value, right? It's going to be, the point is 200 comma 200. And so we search its neighbors. Its neighbors is, 200 comma 0, which we already evaluated to be 200. And its neighbor is 1900, which is, sorry, this point is, I think it's 100 comma 300. And so if you plug in 100 comma 300 into the objective function, you'll get 1900. Again, 1900 is greater than 1400, which means this point is not a local optimum either. So we iterate through to the next vertex. We look at this vertex. So let's look at its neighbors, right? Its neighbor is 0 comma 300. And if you evaluate that into the objective function, you'll get 1800. So now you'll see 1900, this vertex, its neighbors are 1800 and 1400, which means 1900 is a local optimal value. And so once we found this local optimal value, we're done. We're done with our algorithm, right? The pairing that we output is 100 comma 300, which means x1 is 100 and x2 equals 300. Essentially what the solution is saying is that the solution 100 comma 300, when you set x1 to be 100 and x2 to be with 300, this will not only satisfy the constraints that were given, but it'll also maximize our objective function here optimally, right? There's no other point that will both satisfy the constraints and optimally satisfy the objective function. So that's basically a rundown of simplex algorithm. The intuition as to why a local optimal value is also a global optimal value can be shown through this. So let me just erase some stuff. So if you see this point, the point 9 corresponding to 1900, right? Let's graph the objective function that goes through this point, right? And so, treating x1 as x and x2 as y, as you can see in this graph, the slope is going to be what, like negative 1/6, right? So let me just erase this point. So it's going to kind of look like this. Thank God for auto straightening here. So the line is going to, the objective, the line representing the objective function that goes through this point 1900 is going to look something like this, right? This line. And what you'll notice is that all other points in the feasible region that we care about are going to lie kind of underneath this line representing our objective function. And that what that basically means is that now the vertex passing through this line is going to be the optimal value, right? Because why do we know that? We know that because we just extend this further out and extend this further out as well. The two neighbors of this vertex corresponding to 1900 are this one and this one. This one was 1800. So the 1800 point and the 1400 point. Both of these lie underneath the objective, the line representing the objective function. The argument we can extend through this is that we can say that all of the other points in the feasible region and all the other vertices are for sure going to be less optimal than the value corresponding to the vertex that the objective line goes through in this case, right? So that's kind of like an informal way, the rationale behind why the local optimal value is the global optimal value, right? We can just return from our algorithm the moment we find a local optimal value. So yeah, that's the simplest method. And so that's in terms of solving linear programming problems. A few helpful tips, I'd say, when tackling some problems. I've kind of like listed down here, and they're also in the textbook. They're basically variants of LP. How do you go between different linear programming problems, right? So for example, let's say you have a maximization problem as we had here, right? We're maximizing x1 plus 6x2. If for some reason a maximization problem for us is difficult to compute for some reason, and we want to change it to a minimization problem, all you have to do is multiply the objective function by -1. So maximizing x1 plus 6x2 is equivalent to minimizing -x1 minus 6x2. So that's like the first like transformation variant of an LP, right? Another thing you can do is, let's say you have a constraint that says like x has to be greater than a, right? If for some reason you don't like any inequalities, you can change that to an equality by introducing this variable. I think it's called a slack variable. Don't quote me on that, but you can introduce this variable that says s is greater than 0, and then rewrite this inequality x is greater than a into x minus s equals a, right? As you can see, the logic checks out. They're equivalent statements. A third thing is, if for some reason you don't like equalities and you want to change them to inequalities, you can convert x equals a into x is greater than or equal to a, and x is less than or equal to a. So you replace this one constraint with two constraints, right? Because you know if x has to be greater than or equal to a and less than or equal to a, it's going to have to equal a, right? And the last thing, the last kind of mini helpful transformation is, let's say x is kind of unbounded in its sign, right? It can be, you don't know whether it's like negative or positive, or like, it can be any range of values. And let's say for some reason that's really annoying to deal with in a problem. What you can do is you can replace x with two values that are constrained to be non-negative, right? X positive is greater than or equal to 0, and x negative is greater than or equal to 0. And these, you can call these anything like P and Q or A and B. I just like wrote it down. I think the textbook writes it down in this format to make it more logically clear. Oops. So, and then you replace all instances of x with x positive minus x negative. And what you'll see is like, well, that'll basically, it's basically another way of rewriting like all possible values of x, right? Because x positive can equal 3 and x negative can equal 1, and then x will be 3 minus 1, right? Which is 2, which is a positive value. But you can also represent x like negative values of x, right? You can say x positive is 3 and x negative is like 5. Then x is going to be 3 minus 5 equals -2. So you're still representing this entire range of like values that x can take on, but you're doing so with variables that are strictly non-negative. And so again, just maybe might come in handy when you're tackling LP problems. So moving on to kind of like the next topic under linear programming is flows, right? Okay, so flows is kind of like a really interesting problem. It's almost like a case study under the topic of linear programming, right? And the the problem we're trying to tackle is, let's say we have this graph, right? This network, and this is our start, and this is our end, right? And we have these like a bunch of edges and a bunch of edge values. All the edge values, sorry, ignore graph B for now. Just looking at graph A, all of the edge values correspond to the capacities of an edge, right? So I think the textbook the example the textbook gives is like we want to pass oil from S to T, but which is kind of like an obscure example, but a real world application could be like sending packets over the network, right? Let's say you're S and you want to send packets to a friend, like information to a friend T, right, at an end. And so each of these nodes, like A, B, C, D, E, could be like various destinations along the way, um, in the network, right? And each of these edges could correspond to like connections. Like I'm connecting to like one destination in the network, and that communicates, like, let's say I'm connecting with A communicates with D, and then D ends up sending the packets to T, right? And the end goal is I want to send as much information as possible to the end destination, right? To T, right? But the constraints that I have are all of these, various edges, like various capacities, right? So, for example, if I'm trying to send information from S to T, but there's this node A, right? This like middleman, for example, along the way that I have to communicate across. And let's say the capacity, like this, the edge being 3 could mean like at most I can send like 3 packets a minute, um, from S for myself to A, right? And A can send at most like 2 packets per minute, like to D, right? They're just like arbitrary capacities, right? Literally, you can think of them as like a wire, and like you can't fit more than 3 packets across the wire at the same time, or something like that, right? And so, what's our goal? We're trying to maximize the information, or like how much stuff I can send from S to T. And so, kind of like, again, I just kind of wrote that formula here. Like you want to send as much possible from S to T without exceeding the edge capacities, right? We're bound by the edge capacities. And so this sounds like very similar to something we're literally just studying right now, right? This part, send as much as possible, seems like we want to maximize some sort of objective. Um, whereas from S to T, and then this part, without exceeding edge capacities, seems like constraints. And so we can turn this problem of like network flows, sending stuff in a network, into a linear programming problem, right? And so this diagram B kind of like is an example of how maybe you would send oil or information or packets or whatever throughout, right? Since the capacity of S to A is 3, you can send, let's say, like in this example in the graph B, they're sending like two units from S to A. And since S to B is 3, the capacity is 3, let's say they're sending 1, right? And you might wonder, like, oh, why aren't you like sending 3 like throughout S to A and sending 3 to from S to B? Like, why aren't you just sending the maximal capacity out, right? And the reason is because there's all these intermediary edges, right? And we want to make sure we're not exceeding any of those capacities. And so we need to find a way, like we need to send information in a way such that none of those capacities are, exceeded, right? And so kind of framing this formally into a linear programming problem, we get, you know, again, these are just variable definitions. Let's say C sub E is a capacity of edge E, and F sub E is a flow that we're sending through edge E, right? So this diagram, for example, uh, the capacity of C to E would equal 5, um, right? And here oops, sorry, I should have chosen a different edge. Let's just say S to B, right? So the capacity of S to B is 3, as we can see on the left graph. The flow, which is the flow meaning like how much we're actually sending, would be F of E equals 1, right? We choose to send 1, right? And again, we're trying to choose these values, these F values, such that the total information that we can send out is maximized. And so with these variable definitions, let's like go over the constraints first. The first constraint is that 0 is less than or equal to F sub E is less than or equal to C sub E. And this basically means kind of like what this constraint corresponds to in English is don't exceed capacities. And also here I'm saying 0 is less than F sub E because like I'm assuming like you can't send negative flows. But yeah, so again, this constraint basically means like don't exceed the capacities, make sure you're under. The second constraint is this, right? The sum of all, or before I explain the constraint, let's talk about what it actually means. And so this one actually means conservation. What I mean by that is like, let me just erase some of these underlines. What I mean by that is there's all of these intermediary nodes, right? Intermediary nodes, ignoring our start and end, right? And we're going to be sending flow, like sending stuff throughout, like through them, right? Through each node. And basically all the second constraint is saying that whatever flow comes into a node is the same flow that goes out, that leaves it, right? Um, you can kind of see that in the right graph, in the rightmost graph, when we're actually sending flows. Like if you look at node A, like 2 units of flow come from S and 2 units of flow leave A and go to D. And you can do the same for B, like 1 unit comes in, 1 unit goes out, et cetera, et cetera. And again, that's kind of like the second constraint that we care about, right? There's no like flow doesn't just, units of flow like don't just magically disappear, right? And so that's what this is saying, right? Um, this is conservation at a node level. And the actual objective function that we're trying to maximize is this, right? We're trying to maximize like over all of the edges that come out of our start node, we're trying to maximize all the flows through those, right? We're trying to maximize this. And so looking at this example, all of there's 3 edges that come out of our start node, right? S to A, S to B, and S to C. We're trying to maximize the sum of all the flows across these 3 edges, right? Because that represents the total flow. Because due to the principle of like conservation, right? If we send out all of these flows, all these units of flow throughout the edges connected to our start node, they'll go out, they'll be conserved, and they'll in the end they'll reach our end node T. Again, we're trying to maximize this value because that's our objective function. And so Lily will actually cover how exactly we the exact algorithm into tackling network flows.
Thanks, Neil. So now we'll look at the max flow algorithm on the graph. You might be asking, well, why aren't we done? Neil turned the problem into a linear programming problem, and we just covered the simplex algorithm for solving linear programming problems. So supposedly we already have a solution. And you'd be absolutely correct, we do have a solution already. But why are we still here then? It's actually really hard to interpret what the simplex algorithm is doing on the graph in the language of graph and edge capacity since we're dealing with just variables and weights. So in this section, we'll do sort of something similar to that. We'll give a humanly understandable illustration of the network flow problem by, even though it's the same algorithm as the simplex algorithm, it's just a different interpretation and a much more visual and intuitive one. So first, let's look at a naive algorithm. So suppose I just handed you this problem of max flow and I told you, well, flow as many units across as you can. You probably would think of this algorithm right off the bat. It's sort of greedy, right? You take any ST path from the source to the sink, and then you flow as many units as allowed, and then you subtract those units that you flowed from the original graph by saying essentially you can't flow along those paths anymore because those capacities has already been taken. So this sort of hints at an idea of a residual graph, which is just what's left. Like after you have used a bunch of capacities by flowing things across it, you can't use those capacities anymore, so you just subtract it from the original graph. We'll see that this is actually not the optimal way to do it, but it's very intuitive. You flow some units along a path, and then you subtract the capacities that you've already used from the original graph. So let's see how this plays out. Suppose I have this graph on the left side. All of the capacities are 1 for simplicity. And suppose, first thing I do, I find a path from S to T. Okay, suppose I like this one. I go S to A, flow 1 unit across it, and I go A to T and flow one unit across it. So we've flowed a total of 1 unit across, right? 1 unit. And then we see that in our residual graph, we can no longer flow across this S to A and A to T because we've already used them, right? We've used up all of the capacity we could possibly use. So we can erase it. Okay. And now we have this graph. Okay. So let's copy this graph here. This is the graph now. And again, we look for a path from S to T. And now I see I can take this one. S to B, B to T. Okay. And again, we can notate down the original one, the one that we've already taken. So this is our like flow so far. Okay. And this is our residual graph. All right. So now we've taken S to B, B to T, we can erase these as well, right? And we've already taken S to A to T. All right. Now there are no more paths from S to T, and we're done. And it's very obvious that this is, the algorithm that we're looking for. This is optimal. You can flow a maximum of 2 units. And you might be thinking, we're done. Like, this is a happy ending. But here's the problem. This algorithm actually depended on what path we took for the first path. Suppose the first path that I chose for S to T is S to A, and then A to B, and then B to T, and each of them carries 1 unit of flow. Again, this carries 1 unit of flow, but there's a fundamental problem with this. Now, if we look at the residual graph, I took out S to A to B, B to T, and already, even after flowing only 1 unit of flow, we're left with a disconnected graph, and I can't get from S to T anymore. So this means that with this algorithm, if I chose the wrong path, if I chose a wrong flow in the first or at any point, we're sort of screwed. We can't, we've sort of just blocked ourselves off from flowing any more units. So we need to make a modification to this algorithm. This modification is that we want to be able to correct our mistakes. We want to be able to, sort of take back moves. And the way we do this is by flowing backwards. So how do I flow backwards? This is a weird concept, right? So suppose I took the wrong path as I took in the second illustration where I took S to A to B to T as my first move. Then I want to correct myself by taking the following path. I want to take from S to B, B to A, and then A to T. So notice what I did here in the middle. I canceled the downward flow of 1 unit that we took by an upward flow of 1 unit. And you can see that after we do this, we get the following graph. We get, we no longer have this middle guy here. Instead, the only 2 things we have left are S to A to T, S to B, and B to T. And this is exactly what we were looking for in the first place, the sort of correct one that we looked for. So what this means is that we should be able to correct ourselves by reversing flows that we've already taken. What this means is in our residual graph, we not only want to allow flowing along paths that with a remaining capacity that we haven't taken, we should also allow things that flow backwards from flows we've already taken. So more precisely, this means that we can take a path UW in 2 cases. In case 1, we have that there is still flow left, which means CUW minus FUW. So CUW is the capacity, and FUW is the flow so far on that particular edge. is bigger than 0. This means there still remains capacity that we haven't taken. So this looks like, well, how much flow do we still have in our residual graph, or how much are we still left with? Well, it's exactly CUW minus FUW, right? Cool. Now there's a second, so this is not new at all. This is old material. We've always been able to take remaining capacity, take flows along remaining capacity. Now we also want to say we want to take paths with capacity FWU if I have a flow FWU already. So this means if I have this flow from, say, A to B already, then I should be able to take it back with the same weight upwards, right? So this means we can take a flow of weight FWU in the direction of U to W if there's already a flow there. This is taking back flows. I encourage you to pause here and think for yourself why this is important, why we can do this error correcting and why we can take back this flow. All right, so these are the two kinds of edges in our residual graph. So this is UW in residual graph. So what this means for us is that when we're drawing the residual graph, we not only want to draw the ones that we were drawing previously, the ones with a remaining capacity, we also want to draw the capacities on the flow we've already taken, but backwards. Let's see how this works out. So let's copy and paste this graph here. Okay, this is the bad graph that we've already dealt with. So now we want to draw the residual graph in this case. Okay, so the residual graph, SATB, has two kinds of edges. Let's do the first kind first. The first kind is S to B, which still has 1 unit left, A to T, which still has 1 unit left, but everything else doesn't have any units forward. However, because we took the path forward S to A to B, and B to T, we should be able to take it back. So we have a path backwards from A to S, from B to A, and from T to B, each with capacity 1. This allows us to take back our moves. So now when we look at this residual graph and look at what kind of paths we can take, we see that the error correcting path we used is actually on here as a path from S to T. So S to B, B to A, and A to T. So the next we float along that and we look at this residual graph. What does our residual graph look like now? Well, the only place, well, first of all, we don't have anywhere that has a remaining capacity, right? Because after previously we only had S to B and A to T as having remaining capacity, but now we no longer do. Instead, we have these paths that are going backwards. Let's see, going backwards. And then this guy went up, so now it needs to go down. And we can see now that there's no more paths from S to T, so the algorithm terminates. So the algorithm looks something like this. You take flow, like path from S to T, compute residual graph, and then take flow on residual graph. And then you just do these two steps over and over and over again. Repeat. All right, in this last segment, we'll actually compute an example. So I know that there's been a lot of just algorithm talk, and it might help to see a concrete example of how this algorithm works in the wild. So on the left-hand side, I have, well, the graph we're dealing with is on the right-hand side. This is the residual graph, because as you can imagine, at the very beginning, when there's no flow at all, the residual graph is the graph itself, and then the flow so far graph just has nothing on it because we haven't flowed anything. It just has the vertices. All right. So the first thing we do is find a path from S to T. So the first path I want to take is S to A to B, and B to T. It actually doesn't matter which path you take in the first place because of this error correcting we have introduced, but I wanted to take a sort of, I don't know, circuitous route just to show you that in the end we still get a very nice solution even though it looks like this is a very bad choice in the first place. Okay, so once we've taken these paths, I see that on this path I can flow a maximum of 1 unit because uh, the because S to A can only take 1 unit. So even though A to B and B to T can each take 2 units, um, the number of units we can flow is sort of determined by the minimum on that path. So we flow a total of 1 unit across S to A to B, and B to T. So we get this picture right here. You see we've drawn in the flow SA, AB, BT, and now we look at the residual graph. Remember how we first fill in the paths that we didn't really touch. So S to B is copied exactly like before, and A to T is also copied exactly like before. Now we look at the other ones. Remember we said that we want to put in an edge backwards for every edge we traveled along, with weight the same weight as the number of units we flowed. So S to A becomes backwards because after we subtracted that, there are no more units that are naturally you can flow across. So there's nothing from S to A, but A to S, you can take back 1 unit if you want to. Now, as for A to B, we only flowed 1 unit across A to B. So there's still 1 unit left, which is why we have 1 unit pointing from A to B. Now, since we flowed 1 unit from A to B in the previous turn, we want to be able to turn that back. So we put an edge from B to A with weight 1. So this is sort of a miraculous case of having two edges um, going between A and B, and they actually represent the two kinds of edges we can flow across. One is there's remaining capacity from A to B, and the other is we want to be able to take back flow from B to A. Okay, and the same thing goes with B to T. So B to T only got 1 unit flowed across in the last turn, so we still have 1 unit left over in capacity. So B to T has 1 unit. And on the other hand, T to B has 1 unit because again we flowed 1 unit, so we want to be able to take it back. All right. So now that we have this graph, we say, okay, now I want to keep flowing more units from S to T, since I can still reach it. So now I say, okay, let's pick another circuitous route. Let's take S to B, B to A, and then A to T. We can see all the weights are 1, so we flow a total of 1 unit across that. Okay, so now we put this new one in, and as we can see on this flow so far graph, S to A and then B to T didn't really get influenced, but remember on the B to A edge, we took back the previous flow from A to B. So previously we had A to B, but now we took it back, so we no longer have it. And then we add in the S to B and A to T, so these right here. I really highly encourage you to pause if you're having trouble seeing this right now, because this taking back is pretty counterintuitive. So pause it and think through it if you need to. Okay, so now we have this flow so far, and we have the residual. So the residual gets modified by on the path that we took on the previous flow. So S to B gets reversed because there's no more uh, capacity, but you can take it back. And then B to A, we end up getting A to B with 2 units back because we took back that previous unit you flowed. And then we modify A to T to be T to A. All right. So now we look at this graph and see if there are more things that I can flow from S to T. And I say, no, I cannot because S is now a sink. So this algorithm terminates, and we see that on this left side, we have a total of 2 units of flow. And we're done. All right, that's it for this week's mini lecture on oh, actually, just kidding. We have an awesome tutor who will be taking us through one more problem called bipartite matching. It has a lot to do with network flow and is also has a hint of, I don't know, partnership marriage in it if you're interested. So stay tuned for that. And otherwise, I'll see you next week.
Hi everyone. In this segment, I'm going to show you how we can use the max flow algorithm that we've learned to solve a completely different problem called bipartite matching. So the way bipartite matching looks like this. We have a bipartite graph. You can think of these nodes here representing boys and girls, but this can be used in any instance where we need to match one group with another group. So we want to match each boy with a group, and the edges here in this graph represent compatible pairs. So B1 would be happy with either G2 or G3, B2 would be happy with G1 or G3, and etc. So we want to find a matching in this graph that uses only these edges in the graph. And we want to find a matching such that every boy is matched up with a different girl. So this is actually a problem that we can solve using maximum flow. So the way we can solve this is we can put a source vertex here. So we would have a source vertex and then a sink vertex at the end. And the source vertex would have edges going to each of the 4 boys, and then each of the 4 girls would go to a sink vertex T. And then we'll make all of these edges directed edges. So then it can be pretty intuitive to see that any maximum flow, if we can get a flow of capacity 4 in this graph, where each of these edges has a capacity of 1, each of these edges in the middle here also have a capacity of 1, then we can have, if we can get a flow of 4 through this graph, then we can have a matching, because a flow of 4 would mean that each of the 4 boys is matched with a girl, and there's flow going all the way through T. Okay, so one example of such a matching would be, let's say, one flow goes from S to B1 to G3, then to T, and then we have a different color here. S goes to B2, which goes to G1, which goes to T, and then S goes to B3, which goes to G4, which goes to T, and then finally S has 1 unit of flow going to B4, then to G2, then to T. So the matching here in this case would just be the 4 edges that we've used in the center part. So it would be B1 matched with G3, B2 matched with G1, B3 is matched with G4, and B4 is matched with G2. So this is a flow with capacity 4. This is the maximum flow because there's no more edges here to be used. That's 4 is the minimum cut here. So therefore, we can be sure that this is the maximum flow. Now, one question that might arise when we try to run this algorithm is, what if we have integer flows here, but what if there's fractions? How do we interpret that? Well, it turns out when we run the Ford-Fulkerson algorithm, or when we run the simplex algorithm, if we were using linear programming, then if all of the edge weights are integers, then we'll never end up with fractional flows. So in this case, all of the edge weights are 1, and we will end up using a flow of 1 through each edge that is used. So we'll never end up with a fractional flow. So in this case, we have a flow of 4 and we found a matching from it. If a maximum flow of size n is not possible, then we'll never get a matching. And that's because a matching wouldn't be possible in that scenario, because if there was a matching, then we would be able to construct a max flow through this. So this is a nice example of a problem where we can use max flow. We can use max flow to solve a completely different problem that has to do with graphs.
Hi everyone, welcome back to this week's mini lecture / walkthrough. I will be going over a problem in LP known as a diet problem. So in LP in general is optimizing on an objective function subject to linear equality and inequality constraints on decision variables. It sounds like a mouthful, so let's just walk through this pretty simple example to see how one can formulate an LP. Before we start, just a disclaimer, this is absolutely 100% fictional. I have no idea what the actual daily requirements in terms of nutrition are, even though I've taken NutriSci 10. Definitely, I'm not an expert in dieting and nutrition. If you are interested, please visit fda.gov or an official website or source, not me. So this is just for this problem. This is for some living organism living in some civilization on some planet. I just wanted to clarify. We have here two types of food. For food one, it has starch, protein, vitamin values as follows, and the cost per food unit, in this case kilograms, is 60 cents. And then for food two, we have also its starch, protein, and vitamin values, along with its cost per kilogram. So for this very, very specific organism, its daily nutritional requirements recommended are 8 kilogram of starch, 15 kilogram of proteins, and 3 kilogram of vitamins. So far, so good. Our question, however, is to evaluate how much of food 1 and 2 it has to consume every day to meet the requirements specified here at the minimum cost. This is why we have this dollar sign here. With that, let us dive into formulating the LP. I think the most important part is actually just coming up with the different equations and different variables that are needed to give this problem a way to solve it. So it's not in any way an algebra class where you actually have to solve a system of linear equations. Maybe you do very not frequent. So I think this is why I think formulating the LP is actually the most important takeaway from this part of the class. And LP sounds really fancy, but it's actually not that far from solving system of equations or setting it up. And it's probably something you've already seen in algebra / linear algebra. So today we're just going to go over a very simple example with 2 variables. Also, I just gave it away. Whoops. So for step 1, we have to find our decision variables. We have to decide on what unknowns that we have that help us answer this question. How we distribute the money that we have so that we are spending the least amount of money while getting all the daily requirements from food 1 and 2. So maybe you already came up with this, but I will just have 2 decision variables. First one being the number of units of food 1 I will eat per day, and then x2 being number of units of food 2 I'll eat every day. And then the second step in formulating an LP is actually just coming up with the objective function. Sounds very fancy, but the objective function is actually just the question that we're trying to answer. So in order to get the number or the cost that we're spending on the food, we just multiply the unknowns that we have, each of respectively by its cost, and then sum it up together. So our objective in this case is to minimize this summation, which is why it's called the objective function. And this value that we're trying to get is the objective value. The point of this problem is to solve for the amount of food 1 and food 2, but in order to actually solve for the minimum amount of food, we have to actually know how much we would be spending. Yeah. And then the third step, we have to define further constraints. So I think in algebra classes, These two parts are usually enough for us to actually solve for variables. However, especially with solving problems in 170, which sometimes are very real life, and you have constraints that are sort of intuitive and not given to you normally. In our case, we are given, as you can see, a lot of information that we haven't used yet. So this is usually a sign where, okay, like, why did the problem give me more information if I don't use it? So this is where we actually use the nutritional facts of each of the food. So in order to meet our daily requirements, we would have to have enough starch, proteins, and vitamins coming from each of these foods. So how much of food 1 do I need to get, and food 2, to get enough starch for the day? So we have to think about that for all three. So from food 1, as you can see here, maybe writing it in a matrix would be sort of helpful, but just think of it in that structure. If X1 has 5 kilograms of starch, 4 kilograms of protein, and 2 kilograms of vitamins, and X2 or food 2 has 7, 2, and 1 respectively, this is something that we want to maximize because this is the minimum amount of each nutrient that we want. So this is just the additional constraints. And lastly, kind of like in coding questions with base case, where you have to check for pretty trivial edge cases to make sure that the values make sense. We have this constraint called non-negativity constraints. Sort of a tip, but if you ever have to formulate an LP and you have nowhere to start, usually these non-negativity or something related to less than or greater than 0 will probably be on there. This makes sense because you can't have negative amount of food. And in order to solve this, we sometimes look at a graph. And this problem is actually not super complicated because we're only working with 2 unknowns, i.e. 2 dimensions. So you can easily plot this on like Desmos or something. So the next step, we can solve it. And just a couple of definitions. One is the feasible solution, which means that I found some x1, some x2 that not only satisfy all 4 of these constraints we have here written in linear equations, but they also, yeah, that's it. I think it just has to satisfy all the constraints. That's basically the definition of feasible solution. The next part is a lot of times if you have seen in graphs, for example, say I have this line here, one of your constraint is that it has to be smaller than this line. And another constraint is that it has to be greater than this line. So in this case, all possible solutions are contained within this part of your graph. So that would be your feasible space/region. And lastly, if you have a feasible solution that actually achieves the minimum of your objective function value, then that is your optimal solution. And this is what we always want to look for. With this x1 and this x2, in the context of our problem, we're able to find the minimum cost that will get us all the nutrients. And then 2 more definitions. I pulled these from your textbook. One is infeasible. This is when the constraints are like super tight or it doesn't make sense, or it just we just can't really achieve what we are constrained to. So for a very simple example, when x is like, when it has to be less than or equal to -2, or when it has to be greater than 0. This is a toy example. As you can see, there's like no overlap in between them. So this is basically no solution. And then there's also unbounded, when your objective value can get really, really high and there are no constraints. So maybe this one is like under constraint, this one's like over constraint, but there's like not much relationship between those sort of problems. Just another toy example, if you're given the constraint that x1, x2 can be any non-negative integer and we're just maximizing the sum of them, then I think it's pretty clear that there are infinite solutions and we can never find a maximum. So that's basically all I wanted to talk about for the diet problem. I would say definitely go through the textbook to look at the questions on there. They also have really nice graphs accompanying them. Definitely check it out. Otherwise, please post on Piazza or ping us if you have any questions. And hopefully you enjoy this unit. 1, 2, 3, come on, make it bounce.